Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, our energy needs grow exponentially. But our most ambitious projects pale in comparison to the energy output of our Sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we're just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7 distant stars, sparking debate and fueling imagination. Could these signals be technosignatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we have yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres come into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop even more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for technosignatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories, such as the Wide Field Infrared Survey Explorer WISE and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? In the 60s, theoretical physicist Freeman Dyson proposed an audacious idea. An advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar collectors or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. This concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaestus project led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2MASS, and WISE data. Hephaestus uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of stars using Gaia, near-infrared 2MASS observations, and mid-infrared WISE data. This comprehensive data set allows the team to create a detailed model of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaestus has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optics systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the time to search for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hogg found 53 stars with significant infrared excesses. This large-scale search also used Gaia DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample down to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena like dust clouds or the extreme debris disk can also produce similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, and these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals. Biosignatures, on the other hand, are indicators of a biological activity. These can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions for suitable life. It's confirmed dozens of potentially habitable exoplanets in the last year alone. Another important initiative that goes shoulder to shoulder with JWST is the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes such as Webb. Future missions promise to enhance further our ability to detect technosigns and biosigns. The proposed LUVOIR and HABEX missions are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest signs of life or advanced technology. In addition to space observatories, ground-based telescopes like the Extremely Large Telescope and the Square Kilometer Array will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which both have subsurface oceans. Missions such as Europa Clipper and potential future missions to Enceladus aim to detect signs of microbial life in those hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions: are we alone in the universe? All of us probably watched science fiction films and wondered what aliens may look like. Many people imagine extraterrestrial life similar to us, carbon-based, but with a few biological differences. and others imagine it as something completely unlike humans. And so the famous author of The Laws of Robotics, science fiction writer Isaac Asimov, describes some forms of alien life as living stones that had a silicon-based chemical composition as opposed to carbon like us. But what if we told you that silicon-based life may not be entirely fictional? Today we will delve into our biology and try to answer whether the existence of silicon-based life is possible. Carbon is the basis of our life. Without it, it is possible that we would never have come to exist. It makes up about 18%, or 26 pounds of our total body weight, and performs a structural function, forming something akin to a carcass for the molecules and organic substances necessary for our life. Proteins, fats, carbohydrates, sugars, etc., even DNA. Moreover, as you may know, carbon plays an important role for many life forms around us, such as plants. With each breath out, we exhale carbon dioxide. This gas is required for plants for photosynthesis and the production of oxygen as well as organic substances like glucose. CO2 is also the gas that traps heat in our atmosphere, which sustains all life on Earth. If it weren't for the harmful greenhouse effect, we would simply freeze. Aside from the value of carbon and its compounds in biology, it's important to mention the role it plays in manufacturing. Most of the things you see on a daily basis contain carbon. From clothes, medicine, your favorite cup of coffee, and the house you live in, to musical instruments played by your favorite musicians, and the phone or laptop on which you're watching this video. All of it couldn't exist. Of course, carbon is not the only component present in living organisms and all of the aforementioned items, but its chemical versatility and the ability to build huge chains with other elements makes carbon practically indispensable. According to astrobiologist Robert Hazen, a vital chemical element must be able to actively form bonds with other elements and not be too reactive at the same time, so as not to combust during these interactions. Furthermore, this element must form strong, long-term bonds and be able to store and transmit information. Carbon meets these criteria and therefore is superior among the most important building blocks on Earth and beyond. However, is carbon really the only possible foundation for life? What if it was simply erased from outer space? What element could then replace carbon? The possible answer can be found right under carbon in the periodic table: silicon. Silicon is one of the most common elements on Earth. Its core contains about 28% of its total mass. This element can be found in sand, amethyst, clay, granite, etc. Like carbon, silicon has a wide range of applications and is a valuable element in our life. Many processors in phones and computers use silicon as an accessible alternative. Silicon is also used to form conformable silicone compounds, which have applications in cosmetic and medical industries, ranging from hair conditioners to contact lenses, as well as aviation and construction spheres, like in sealants and nonstick paint. So what role does silicon play in our biological life? According to researcher Milton Wainwright, it's likely that silicon may have had an effect on the emergence of life on Earth. According to his research, silicon that comes from outer space may stimulate bacteria growth, even if there's a lack of nutrients. The scientists therefore suggest that billions of years ago, during the birth of the solar system, comets containing silicon may have bombarded Earth, which caused the development of bacteria. In addition to its possible merits in the past, silicon is also a very important component in plant development and growth. Silicon protects plants from external threats, both physical and chemical, making them more resistant. It also protects the plants from disease and prevents them from losing water. Moreover, silicon is important for healthy bone development and wound healing in humans and other animals. This element may also reduce the risk of Alzheimer's and cardiovascular disease. You could say that silicon, in fact, has an auxiliary effect on our lives. So why is it being considered as a likely alternative for carbon in alien life? First, it is due to their chemical similarity. There is a reason why silicon is located right under carbon in the periodic table. Each chemical element in the table can form a chemical bond, during which the electrons of each atom are combined. Silicon and carbon are both tetravalent, meaning they can bond to 4 atoms. As such, silicon can probably form long and strong bonds with different elements, similar to carbon. Secondly, in 2016, a team of scientists from the California Institute of Technology, led by Francis Arnold, were able to synthesize molecules that are made entirely of silicon and carbon. Furthermore, according to their study, E. coli could produce the protein that contained this compound. Scientists came to the conclusion that silicon-based life is possible outside of Earth. So, in order to answer the question of whether silicon could replace carbon, we must first consider what life is in biological terms and what are the criteria for it to occur. Scientist Norman Pace believes that life is the ability of an organism to replicate itself and to develop enough to overcome evolutionary hurdles. For example, developing the ability to grow organs required for movement in order to make travel across land easier. Therefore, the building blocks of this organism must be able to quickly adapt to new conditions. In addition to chemical complexity, a number of ecological criteria must be met for life as we now know it to emerge. In short, life requires oxygen, nitrogen, moderate temperatures, and water. Many compounds are highly soluble in water, such as salt. Therefore, previously separate parts of one compound can create new bonds with other elements. Carbon can form a long and stable framework for the living cells of water-based organisms. But can silicon also make connections necessary for life to exist? The short answer is no. So, what? That's it? Silicon-based life cannot possibly exist? Not quite. Because in addition to water, there are other solvents in which life can hypothetically originate. For example, scientists speculate that liquid ammonia, which is common on Jupiter and Pluto, could serve as an alternative to water. However, NH3 is highly toxic, which may prevent silicon-based life from developing, but scientists have yet to test this theory. In addition to liquid ammonia, another potential solvent is sulfuric acid. You may note that H2SO4 is generally capable of dissolving most metals without residue, and you'd be correct, but oddly enough, it's also possible for silicon to develop in it. Therefore, hypothetically, silicon-containing organisms can develop on planets with a sulfuric acid environment, such as Venus. Silicon can also exist in other cold solvents like methane and ethane, which become liquid at low temperatures, as they do on Titan, one of Saturn's moons. However, low temperatures greatly slow down any chemical processes and solubility. Although silicon would be able to quickly combine with other elements at low temperatures, silicon compounds would not be able to dissolve very quickly. Therefore, it would be very difficult for life to emerge in such conditions. But what about the structural function of silicon? Just like carbon, silicon can combine with elements essential for our existence, including nitrogen, hydrogen, oxygen, phosphorus, sulfur, and even many metals. However, silicon is not as versatile and adaptable as carbon. In addition to the fact that silicon cannot develop in water, it will also not bond with anything at moderate temperatures between 32 and 212 degrees Fahrenheit. That means that silicon can only combine with other elements at excessively high or significantly low temperatures, which would make it very difficult for other elements to build bonds with silicon. Moreover, unlike carbon, silicon does not bond well with itself, and that is the bonds between two silicon atoms that would not be able to build a very large framework for cells. Think of a diamond. It's made entirely of carbon, which shows the strength of the compounds the element is able to form. However, the one element that silicon likes to combine with is oxygen. And this further supports the theory that silicon-based life is unlikely. On Earth, silicon is almost always found in the form of SiO2, which is basically sand, making it very difficult to separate the two elements. This means that silicon is less versatile than carbon, which forms equally strong bonds with other elements. Turns out that if we could swap carbon in our body for silicon, then instead of carbon dioxide, we would exhale sand. Aside from respiration, carbon also plays a very important role in our nutrition. Food is an excellent source of energy, which is why when we feel tired, there's nothing better than a good meal. However, our source of energy is not the food itself, but the compounds it contains, like glucose. As you may have already guessed, glucose is also made of carbon. What's more, when we don't have an opportunity to eat and we need energy, another carbon compound like starch can help us. It's deposited into the liver and used to replenish our supply of glucose when needed. However, these bonds would be unstable with silicon, which means they would not be able to properly support our life. While silicon is unlikely to replace carbon, it is possible for silicon-based life to evolve. However, it's highly doubtful that an organism that only contains silicon and no carbon in its chemical composition would be able to build complex chemical bonds. Silicon-based organisms have not yet been found on Earth, but as we've already mentioned, silicon is an important secondary component for many plants and animals. In some ways, it could probably be considered a part of ourselves. Furthermore, our ocean contains diatoms, a type of mysterious algae with cell walls made of transparent SiO2. This doesn't make this algae a silicon-based life form, but it does prove that silicon can indeed act as a building block of a living organism. As for other planets, according to a study by a team of scientists led by Ricardo Gobato, the ideal environment for the development of silicon-based life are the virtual absence of oxygen and water, temperatures above 428 degrees Fahrenheit or below 32 degrees Fahrenheit, atmospheric pressure much higher than on Earth, and a solvent like sulfuric acid or methane. Some of the planets in the solar system fit some or almost all of the criteria. For instance, Titan, the largest moon of Saturn, and possibly Venus. Titan has a multitude of methane and ethane lakes, as well as a nitrogen atmosphere, which are both excellent conditions for the origin of silicon-based life. The surface of Venus is very hot and subject to high pressure. However, the thing that makes Venus one of the candidates for silicon-based life are yellow clouds of sulfuric acid present on the planet. Hypothetically, silicon organisms could form in these clouds, although most likely, even on Venus, a molecule like that would contain significantly more carbon than silicon due to the high content of carbon in the atmosphere. Surprisingly, another candidate for the formation of silicon-based life are hypothetical carbon planets. At the moment, scientists only know of one such exoplanet, 55 Cancri e, which is located 40 light-years away from Earth. These planets likely form further from their parent star, which means they may have solvents suitable for silicon on their surface, and hypothetically, no water either. Moreover, it is possible that carbon planets are full of heavy hydrocarbons like butane, which may be suitable for silicon-carbon bonding. However, silicon-carbon compounds, silicon carbide, are very strong. which means their decomposition can take a lot of time and energy. So even if life begins to develop on a carbon planet, it will be a very long process. If we assume that silicon-based life has in fact existed for some time, then how would we recognize it? Sci-fi writers imagine a life form similar to living stones, like the authors of the Star Trek, for example.
We are dealing with a silicon creature of the deep rocks.
However, in reality, silicon-based life does not necessarily look like this, since we are also not covered in diamonds and diatoms look nothing like stone. The fact of the matter is, scientists have no idea what a silicon-based life might look like. However, they assume that silicon-based life is unlikely to resemble us in chemical complexity or even intelligence, so we probably won't get to meet stone people. Such alien organisms would also be difficult to find if not technologically advanced, because we simply would not know what molecules to look for. It is difficult for humans to imagine the possibility of life developing in conditions that are significantly different from those on Earth. The only life we've encountered so far is ourselves and the creatures surrounding us, which is why most missions sent into space focus on finding structures similar to our own. Right now, it's impossible for us to know if there is life made predominantly of silicon due to our scientific limitations. However, the cosmos is vast and diverse, so we cannot say for certain whether all alien life in billions of galaxies is carbon-based. Ever since telescopes reached the stars, humanity has been consumed with the search for life beyond Earth. We've sent rovers to Mars, probes to Venus, and even peered into the icy oceans of Jupiter's satellite, Europa. But all these efforts have been guided by a single assumption. Life, wherever it exists, must be something like us, carbon-based and dependent on water. This is where the concept of the Goldilocks zone comes into play. This is a neither too hot nor too cold region around a star where conditions are just right for liquid water to exist. For decades, this zone has been the center of our extraterrestrial search, the celestial point where we believe life is most likely to thrive. From the Viking landing modules on Mars to the Voyager probes traveling beyond our solar system, the hunt for extraterrestrial life has been a hunt for Earth-like conditions. We look for planets with atmospheres similar to our own, signs of water or ice, and even certain gases such as methane and oxygen that might indicate biological activity. But what if this geocentric approach has narrowed our vision? What if, in our search for a mirror of our world, we've overlooked vast expanses where life might exist, but in forms radically different from our own? It's a humbling thought that challenges the very structure of astrobiology. After all, if life can exist without water, then the Goldilocks zone is not the only area in the cosmic real estate market where life can settle. And that brings us to ammonia, a molecule that has long been relegated to the background but is now taking center stage in a potentially game-changing way in our search for life beyond Earth. Did you know that ammonia, a compound you might associate with cleaning products, has a lower freezing point than water, enabling life in an extremely cold condition? Or that ammonia can dissolve a wide range of organic compounds, potentially serving as a medium for various types of biochemical processes? When we think of life, we often envision Earth's blue-green tapestry, forests teeming with wildlife, and oceans filled with a multitude of marine life. But what if there are shades in the palette of life that we haven't even realized? What if beyond the azure oceans and emerald forests there are worlds where life thrives in a golden sea of liquid ammonia? So, venturing beyond the familiar territories of carbon and water, we encounter a molecule that has long been in the shadow of astrobiology: ammonia. This humble molecule, composed of just one nitrogen atom and 3 hydrogen atoms, may hold the key to a life form quite different from our geocentric definitions. At first glance, ammonia seems an unlikely candidate for life support. After all, we're used to thinking of it as a caustic gas, a household cleaner, or an industrial chemical. But when we delve deeper into its chemical properties, a different picture emerges. Like water, ammonia is a polar molecule capable of dissolving a wide range of substances. It can act as a solvent, facilitating complex biochemical reactions, just as water does on Earth. However, ammonia operates under different rules. It has a lower boiling point and a lower freezing point than water. This means that life based on ammonia will exist at temperatures much lower than any earthly organism can tolerate. Imagine a world where the average temperature is well below freezing, but life thrives in oceans of liquid ammonia. Such a world would not only have a different biochemistry, but also different color palette. The sky may have shades of orange and red, and the seas may shimmer with hues of gold or bronze. Very different from the blue and green landscapes we associate with habitability. And just as there is a water cycle on Earth, an ammonia-based world will have its ammonia cycle, complete with ammonia clouds, ammonia rain, and perhaps even ammonia snow. This active cycle would be essential for any potential life forms, providing a dynamic environment for development. If life can exist in Earth's extreme environments, from acidic lakes to deep-sea hydrothermal vents, why not in the ammonia-rich landscape of distant exoplanets? This possibility has the potential to rewrite textbooks and push the boundaries of life as we know it. As we delve deeper into the realm of alternative biochemistry, it's critical to distinguish between 2 key components of life: carbon and water. While both are essential for life on Earth, their roles are distinct, and understanding this difference is crucial when we consider the possibilities of ammonia-based life. First, let's talk about carbon. Carbon is the basis of all known life forms, a versatile element capable of forming complex, stable structures such as proteins, lipids, and DNA. Its ability to form 4 bonds makes it uniquely suited to create the complex molecules that are the building blocks of life. Now let us consider water. Water acts as the stage on which the drama of life unfolds. It is a solvent that facilitates biochemical reactions, allowing molecules to meet, interact, and transform. In essence, if carbon is the actor, water is the theater itself. So what happens if we replace one of these key players? Replacing carbon would mean rethinking the very building blocks of life, a feat that seems almost insurmountable given carbon's unique properties. But what happens if we replace water with ammonia? That's a different story. Ammonia can also act as a solvent, albeit in a colder temperature range, offering an alternative step in the biochemistry of life. As with water, the polarity of ammonia allows it to dissolve various substances, making it an acceptable alternative for facilitating biochemical reactions. However, because of the lower temperatures, reactions are likely to be slower, potentially leading to life forms with a slower metabolic rate.
In an ammonia-based world, cells may have membranes composed of lipids stable in ammonia and enzymes that catalyze reactions in this alternative solvent. The genetic material may still be similar to DNA or RNA, but adapted to an ammonia-rich environment. So when we ponder the possibilities of life beyond Earth, the question is not only where to look, but what to look for. Let's delve into the biochemistry of an ammonia-based life form. In such an organism, the role of water as a solvent would be replaced by ammonia. What about the biochemical reactions themselves? Can the enzymes and proteins that facilitate life processes in aquatic organisms adapt to an ammonia-rich environment? The answer is staggeringly possible. Enzymes, biological catalysts, may have evolved to function at lower temperatures and in the unique chemical environment provided by ammonia. These enzymes may be composed of amino acids stable in ammonia, allowing metabolic processes to occur, albeit at a slower rate due to the colder conditions. But what would these life forms look like? In an ammonia-based world, we might find organisms with biochemistry and physiology radically different from our own. Imagine creatures with flexible, elastic skeletons adapted to lower gravity and lower temperatures, or plants that use a different pigment for photosynthesis that absorb and uses light more efficiently. For example, a pigment that absorbs blue or violet light may be more efficient if a planet orbits a star that emits light predominantly in those wavelengths. In designing future space missions, these considerations could be critical. Instruments capable of detecting not only water and oxygen, but also ammonia and other biosignatures would expand our search parameters and allow us to explore these exotic possibilities. The implications of ammonia-based life go far beyond scientific curiosity. They could fundamentally alter our approach to the search for extraterrestrial life by changing the strategies and technologies we use in this great cosmic quest. So far, the parameters of our search have been strongly influenced by our geocentric perspective. We've aimed our telescopes and sent probes to places where we expect to find Earth-like conditions. But if ammonia-based life is possible, then our search field expands exponentially. This means rethinking mission objectives and scientific instruments. Future space probes may have to carry detectors sensitive to ammonia and other non-aqueous solvents. Spectrometers may have to be calibrated to look for unique spectral characteristics of ammonia-based biomolecules. Imagine a new generation of Mars rovers designed to probe the icy satellites of Jupiter and Saturn, not only for water, but for pockets of liquid ammonia. Or orbiters equipped with advanced sensors that can analyze the atmospheres of exoplanets in search of chemical imbalances that might indicate ammonia-based biological activity. The discovery of even ammonia-based microbial life would be a revolutionary event that would leave a lasting impression on the world and change our philosophical and ethical foundations. How would such a discovery affect our understanding of the uniqueness and commonality of life in the universe? What ethical considerations might arise from interacting with or studying these alternative life forms? Education will also transform. Future biology textbooks may include chapters on alternative biochemistry, and astrobiology may become a standard part of educational programs, inspiring a new generation of scientists to think beyond Earth's limits. As we stand on the threshold of this new frontier, the implications of recognizing ammonia as a potential cornerstone of life are enormous. It broadens our horizons, challenges our assumptions, and opens up a universe full of possibilities. Possibilities that may start with a simple molecule, but lead us to worlds beyond our wildest imagination.
Do you think it could be that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the omnipresent force that apparently governs our existence and dictates the rhythm of our lives, is not what it seems. For example, time appears to be slowed down for an object moving close to the speed of light, and it flows at different speeds depending on the strength and the gravitational field around us. Have you ever considered that time may be just a figment of our imagination, a construct invented by our brains to make sense of the world? In search of the truth behind this mysterious concept, you'll have to step into the unknown and question everything you thought you knew about time. Time, in its simplest form, is a tool we created to measure change and put order into the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles such as day and night or the changing of the seasons. This was crucial to the coordination of activities such as farming, navigation, and religious rituals. Early methods of timekeeping were based on natural phenomena, such as the rising and setting of the sun, the phases of the moon, and the position of the stars. As human society became more complex, so did our methods of measuring time. We developed tools such as sundials, water clocks, and finally, mechanical clocks to divide the day into smaller and more manageable parts. Calendars were created to track the passage of longer periods such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of human understanding and interpretation of time. While timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brains process and interpret time differently depending on factors such as age, emotional state, and cultural background. This suggests that time is not a specific universal phenomenon, but rather a flexible construct that we shape according to our individual experiences and needs. Despite its ubiquitous presence in our lives, time remains a somewhat illusory concept. This raises the question: is time an objective reality, or is it simply a construct we've created to order the chaos of our existence? So let's delve a little deeper into history. The traditional understanding of time as an independent, constant entity was challenged by a groundbreaking work from the early 20th century written by Albert Einstein. Einstein's theory of relativity introduced the concept of time as a dimension, forever changing our view of this mysterious phenomenon. Einstein's theory of relativity emerged from his work on the nature of light and the concept of absolute space and time, which was central to classical physics. He proposed that the law of physics should be the same for all observers, regardless of their motion relative to each other. This revolutionary idea led to the development of two interrelated theories: the special theory of relativity and the general theory of relativity. In the special theory of relativity, Einstein demonstrated that space and time are not separate entities, but intertwined in a single continuum known as space-time. In this four-dimensional structure, time becomes the fourth dimension, and events are represented as points in space-time. This concept shattered the traditional view of time as an independent variable by showing that it is an integral part of the fabric of the universe. Einstein's theories also showed that time is relative and dependent on the observer's frame of reference. According to the special theory of relativity, two events that appear to be simultaneous to one observer may occur at different times to another observer moving relative to the first. This phenomenon, known as simultaneity relativity,
challenges our perception of time as an absolute and constant entity. The general theory of relativity extended the ideas of the special theory of relativity to include gravity in the picture. In this theory, massive objects such as planets and stars cause space-time to warp, and this warp is perceived by objects moving within it as gravity. The presence of a massive object can also affect the flow of time, leading to a phenomenon known as gravitational time dilation. In the special theory of relativity, time dilation occurs when two objects move relative to each other with considerable speed. The faster an object moves, the slower time flows for that object compared to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. This phenomenon is best illustrated by the famous twin paradox, where one twin travels at near the speed of light, while the other stays on Earth. Upon return, the traveling twin will be younger than the Earth twin because of the time dilation. In general relativity, time dilation is also due to the influence of gravity. Time flows more slowly in stronger gravitational fields, for example, near massive celestial objects such as planets or stars. This effect has been experimentally tested using atomic clocks placed at different heights. Clocks closer to the Earth's surface, where gravity is stronger, run slower compared to clocks at a higher altitude, where gravity is weaker. The slowing of time, while seemingly illogical, has been confirmed experimentally and has practical applications. An excellent example is the Global Positioning System, or GPS. GPS satellites orbiting the Earth experience time dilation based on both velocity and gravity, which must be taken into account to maintain accurate timekeeping and location data. In addition, experiments with high-speed particle gas pedals have confirmed that particles traveling at near light speeds experience significant time dilation, as predicted by the special theory of relativity. Before Einstein's theory of relativity, time was assumed to be unchanging and a universal background for all events in the universe. Sir Isaac Newton, for example, believed in the concept of absolute time, which flows uniformly and independently of the events he measures. However, the discoveries of time dilation and the relative nature of time in both the special and general theories of relativity challenge this concept, demonstrating that time is not a constant but a variable, depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also assumes a strict adherence to causality, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events may depend on the observer's frame of reference, which can lead to situations where cause and effect may appear to be reversed or simultaneous. This challenges our intuitive understanding of causality and forces us to re-evaluate how we think about the evolution of events in the universe. The concept of the arrow of time, the idea that time flows in one direction from past to future, that's deeply rooted in our understanding of the world, has also been challenged. However, the findings of relativity theory regarding the relative nature of time and the potential reversal of causality prompt us to reconsider whether the arrow of time is a fundamental aspect of the universe or simply a construct of human perception. Since the traditional view of time as an absolute entity has been undermined by the discoveries of the relativity theory, some scientists and philosophers have suggested that time may be an emergent property rather than a fundamental aspect of the universe. From this perspective, time arises from interactions and relationships between objects and events, rather than existing independently. Leaving behind the challenges of Einstein's theory of relativity, we venture into the even more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and elusive, as the rules governing the quantum world defy our everyday understanding.
Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic levels. It's governed by a set of probability rules that are markedly different from the rules of classical physics. In the quantum world, particles can exist in several states simultaneously, a phenomenon known as superposition, and their properties are defined only when they're measured or observed. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics described time as a continuous and absolute entity, quantum mechanics treats it as a discrete, quantized parameter. This leads to situations where it seems that time loses its traditional meaning and takes on a more abstract role. Now, to illustrate, let's consider the following everyday scenario. You observe animals in the wild and notice they behave differently when they know they're being watched. The closer you get to them, the more their behavior changes, making it difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also called the Heisenberg uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can disturb the state of a quantum object, such as an electron. Just as your attempt to observe animals in the wild affects their behavior, observing or measuring a quantum object can affect its properties, such as position or momentum. Heisenberg's uncertainty principle states it's possible to simultaneously know the position and momentum of a quantum object with absolute accuracy. The more precisely we measure one property, the less precisely we can know the other. In the quantum world, the very act of observation or measurement can lead to the collapse of the wave function of a particle and the transition from the superposition of many states to one definite state. This process is inherently probabilistic, and the result cannot be predicted with certainty. Taking into account the phenomena of quantum superposition and observer effect, it becomes obvious that our traditional understanding of time as linear progression may be wrong on the quantum level. Instead, the quantum world offers a more fluid, interconnected view of time where the boundaries between past, As we've seen, our understanding of time is closely intertwined with our understanding of space, and this complex relationship has given rise to many theories attempting to explain the nature of space-time. Among these theories, one stands out as particularly intriguing and thought-provoking: the block universe theory. The block universe theory, also known as eternalism or the space-time block view, is a philosophical concept that stems from our understanding of Einstein's theory of relativity. According to this theory, past, present, and future are not separate entities, but part of a single four-dimensional structure called space-time. In this structure, all events from the origin of the universe to its possible end coexist simultaneously. To better understand the theory of the block universe, we must first understand the concept of space-time. In Einstein's theory of relativity, space and time are intertwined, forming a single continuum. Space-time can be thought of as a vast four-dimensional block containing every event that has ever happened or will happen. In this situation, time is not a separate dimension that flows linearly, but rather an integral part of the space-time structure. Each point in space-time represents a unique event, and all space-time encompasses all possible events. Consequently, past, present, and future coexist in a block universe, turning our perception of time as a linear progression into an illusion created by our limited perspective. In the block universe theory, observers play a crucial role in the perception of the flow of time. Our perception of time as a linear progression from past to present to future is the result of the movement of our consciousness along our world lines, the paths we trace in space-time. Although all events exist simultaneously in the block universe,
sense of time is limited to a single point on our world line, the present moment. This subjective sense of time can be likened to reading a book. Although all the words and sentences exist simultaneously on the pages, our perception of history is sequential, revealing one word at a time. Similarly, the events of our lives unfold as we cross our world lines with the block universe. Block universe theory also raises thought-provoking questions about the nature of free will. If all events, including our thoughts, decisions, and actions, are predetermined and exist simultaneously in space-time, does this mean that our choices are predetermined and free will is an illusion? This question has been the subject of heated debate among philosophers and scientists alike. Some argue that the existence of free will is compatible with the block universe theory since our choices can still be determined by our internal processes, even if the results are already fixed in space-time. Others argue that a block universe implies a deterministic universe where our actions are simply the result of the laws of physics and the concept of free will is an illusion. Not only does the theory of the block universe challenge our understanding of time and causality, it also raises profound questions about the nature of reality itself. If all events coexist in space-time, does this mean that reality is a static, unchanging structure? Or is our perception of reality, including the subjective flow of time, an essential aspect of the universe that cannot be separated from the objective structure of space-time? These questions go to the heart of our understanding of the nature of existence. By exploring the implications of block universe theory, we may be forced to reevaluate our perceptions of time, causality, free will, and reality itself, opening the door to a new understanding of the fundamental nature of the universe. In our daily lives, we rely on the passage of time to structure our activities, make sense of the world around us, and create meaningful accounts of our experiences. Time allows us to perceive change, growth, and decline, and to make predictions guided by past events. At the same time, our study of the nature of time has shown that our perception of time as a linear progression may only be a simple illusion, the product of our limited perspective in the vast fabric of space-time. This paradoxical nature of time is a fascinating enigma. Time is both an important aspect of our lives and a construct that may not exist as we perceive it. Either way, we must remain open to new ideas and perspectives, for it's through our curiosity, our willingness to question the nature of reality, and our relentless pursuit of knowledge that we will continue to discover the mysteries of time and the universe itself.